example, we were going to use KVL and KCL to solve the problem. Okay, so we can use equivalent resistance, we can use multiple methods, but again, our first is Kirchhoff's KVL is Kirchhoff's voltage law, and this is Kirchhoff's current law. We have a one source circuit with a couple of resistors in parallel and some combination, and we have our voltage R1, R2, R3 is equal to R1, which is 5, R4 is equal to R2, which is 10. Now, the beauty of KVL and KCL is it's not important if you have to know if resistors are series or parallel and make all these geometric determinations. You simply just have to follow the system. If you follow the system, the answer always comes out, right? So here, the first thing we're going to do, okay, in any of these systems, you simply draw in the current loop. Now, really, for our intents and purposes, we learned that the current loop generally goes from negative to positive, which is true, because if it's one source, it's easy to determine that it's going to flow in this direction, right? That's easy. And we're going to call this I1 of loop 1. On the right-hand side, we can assume it can go this way, it can go another way. We really don't know, okay? But let's just assume this direction, okay? For complex circuits, there's no way to know which direction the current flows. But for a simple circuit like this, especially in loop 1, you will know that it's going to flow in this direction, okay? So first thing we do is that. Then what we observe is how it goes into the nodes. So we identify the nodes. Here's loop 1, loop 2, and here are the nodes. Now these two nodes are going to be the same, so we're just going to say node A, okay? At node A, current is is going to loop like this. It's the path of the current. And at the path of the current is going to obviously come into the node, right? Very straightforward. Here, I2 is moving around this way and is going to go out of the node. Okay. So what's left? Well, there's only one other current left, and this is the combination, right? I1 runs from here to here. I2 runs from here to here. I1 and I2 in combination run from here to here. So you simply write that in, okay? And this is just an assumption, okay? If I get a negative value, I assume the other direction, okay? So it's very simple. So what we're going to do is, then what we do is we analyze. Well, let's just start with loop 1. And we type in loop 1, and we type in KVL, write in KVL, sorry. And when we analyze this loop of KVL, we write sum of the voltage around the loop is equal to 0. Okay? That's the definition of KVL. Now, the current as it flows from over R1, we're going to assume a voltage drop. Now, a voltage rises from minus to positive, a drop is from plus to minus. It's going to drop, high to low, okay? And since this is R1, we're going to call this V1, okay? And here, we're going to look at I2. And I2 is going to obviously, and I'm running out of space, so I'm going to write off to the side. Up here is going to go from high to low here. We're going to call it V2 with respect to R2. And I2 comes around here and is going to drop V4, just like that. Okay? Now, in this node here, I3 is going to drop here. So it's the dominating current. The dominating current in this area here is I1. So it determines the polarity over R. The dominating current in this area here, okay, in this little part here, is I2. So it will determine the drop of R2 and R4. The dominating current in I3 on KCL is going to drop here. Okay? So based on that, we're going to use sign convention. Use the first sign or second sign. Now I'm going to use the second sign. Okay? You can use the first sign. You'll still get the same answer. Okay? So what we're going to do is we're going to circle as the current travels. So I generally start from here for the simplest node first, simplest component first. So I go up here, say, okay, it's the second sign, and I come back around the loop, second sign. This is my voltage loop here, okay? And what I do is I just write it out. Plus Vs minus V1 minus V3 equals 0. Then I start looking at the problem a little more closely. I know that this is my source. I leave it alone. V1 is my I and R1. I1 runs over here. Okay, right here. I1 and R1 are here. So this resistor has I1, R1. This resistor here, this voltage across this resistor here is I3, R3. Okay. Now I simply plug in the numbers. Vs. Let me erase this real quick. Vs is 10, right? So from here, you know our Vs value is 10. 10 minus I1, 5. I3, R3, which is R1, which is equal to 5, equals 0. That's going to give us minus I1 times 5 minus I3 times 5 is equal to minus 10. I flip the 10 to the minus side. This is algebra. So 5I1 plus 5I3 is equal to 10. This is an algebraic component. Okay? This is equation 1. Okay. We do the same thing for this loop. Okay? Loop 2. KVL. Second sign. Okay, so just wanted to kind of be clear on this. This is a bit of a long problem. So I'm going to go back and forth from the equation to the diagram so that you can follow. If you have any questions, please, if this diagram goes off the page or the equation down here goes off the page, simply just adjust just hit reverse. I'm going to go back and forth like that. Hit reverse or pause on the video so you understand you can rewind it, okay? So we do the same thing as we did up here, okay? Sum of the volts around the loop is equal to 0, which will imply, okay, you will start here on loop 2. Use the second sign, right? And then second sign here. Okay? So if we go down a little bit, we see second sign, because this is the path of the current. Okay? So from here, minus V2, just like here. Minus V4, just right here. Plus V3 is equal to 0. Okay. Now I simply replace the values. V2 up down here is up here, which is I2 R2. Just off the diagram, I write I2 R2 minus I2 runs here over V4, so I2 R4. I2 R4 plus R3 has I3 R3. Okay, so for V3 it's I3 R3 equals 0. Okay, so what we start doing now is we start plugging in the values, right? We know that R2 is 10, R3 is equal to R1, which is 5, and R4 is R2, which is 10. And you simply plug the values in. Okay? So minus I2, R2, which is 10, I2, R4, which is 10, plus I3, R3, which is 5, is equal to 0. You just simply combine the terms. Minus 20 I2 plus 5 I3 is equal to 0. This is your second equation. Okay? And you'll have one more equation, which I will do side by side. Okay? The last equation you'll have is off the node. Okay? So here, I'm going to operate side by side. So here we see node A. Right? So we're going to write in node A. But node A is KCL, which is Kirchhoff's current law. And Kirchhoff's current law is very easy. Simply assume a direction into the node. So what we're going to do is sum of the current going into the node is positive. Now I can assume going out of the node, but this node, this little dot represents this intersection here. This arrow represents this I here, this current here. If this current is going in, this current is going in, just like that, okay? That means that your current is positive. This whole summation is equal to 0. How do I apply this? Very simple. Is I1 going into node A? Yes. So it's I1 plus I1. Is I2 going in or out of node A? I2 is pointing out of node A, so that's minus I2. Is I3 going in or out of node A? Well, I3 is obviously going out of node A, which is minus I3. That's equal to 0. Okay? So I1 is equal to I2 plus I3. This is your third equation. Okay? The way to solve this, here are your three equations. Like so. Okay? Equation 1, equation 2, equation 3. The way to solve this is simply, you have I1 equals I2 plus I3. Take this and put it in here and solve. And we will solve these equations in later videos. But this is how you set it up.